Hello everyone. We have discussed the algebraic properties and the order properties of the real number system in the set theory playlist. In this video we will present one more property of R that is called the completeness property. We now introduce the notions of upper bound and lower bound for a set of real numbers. Let S be a non-empty subset of R. A real number U is called an upper bound of S if S is less than or equal to U for all S in the set S. S is said to be bounded above if S has an upper bound. A real number W is called a lower bound of S if W is less than or equal to S for all S in the set S. S is said to be bounded below if S has a lower bound. A set is said to be bounded if it is both bounded above and bounded below. If S is bounded above, then a number U is said to be a supremum, or a least upper bound, of S if U is an upper bound of S, and if V is any upper bound of S, then U is less than or equal to V. If S is bounded below, then a number W is said to be an infimum, or a greatest lower bound, of S if W is a lower bound of S, and if T is any lower bound of S, then T is less than or equal to W. Let's prove a lemma. An upper bound U of a non-empty set S of R is the supremum of S if and only if for every epsilon greater than 0, there exists S1 in S such that U minus epsilon is less than S1. For the forward direction, let U be the supremum of S. Let epsilon be greater than 0. Then U minus epsilon, which is less than U, is not an upper bound since U is the least upper bound. So the statement S is less than or equal to U minus epsilon for any S in the set S is false, which is equivalent to saying that there exists some S in the set S such that S is strictly greater than U minus epsilon. For the backward direction, suppose for every epsilon greater than 0, there exists some S1 in S such that U minus epsilon is less than S1. Then we have the statement for any S in the set S, S is less than or equal to U minus epsilon being false. So U minus epsilon is not an upper bound for any epsilon greater than 0. Combining with U as an upper bound, we have U as the least upper bound of S. It is important to realize that the supremum of a set may or may not belong to that set. Define a set A to be the set of real numbers between 0 and 1. 1 is an upper bound of A. Let epsilon be greater than 0. Take the average between 1 minus epsilon and 1. Then 1 minus epsilon is less than 1 minus epsilon over 2, which is less than 1. As S1 is defined to be the maximum of 1 over 2 and 1 minus epsilon over 2, which belongs to A and 1 minus epsilon is less than S1, we have the supremum of A is 1 by the lemma. Similarly, the infimum of A is 0. Note that both the supremum and the infimum of A belong to A. Define a set B to be the set of real numbers strictly between 0 and 1. 1 is an upper bound of B. Using the same argument, we see that the supremum of B is 1. In this case, B does not contain its supremum. Similarly, the infimum of B is 0, which is not contained in B. Finally, let's state the completeness property. Every non-empty set of real numbers that has an upper bound also has a supremum in R. From this, we can show that every non-empty set of real numbers that has a lower bound also has an infimum in R. Suppose T is a non-empty subset of real numbers that is bounded below. Then the non-empty set T2, which is defined to be the set of negative T's, is bounded above. By the completeness property, U, which is the supremum of T2, exists in R. You can verify that the infimum of T is equal to negative U. This is the end of the video. If you find my videos interesting, please consider subscribing my channel, liking my videos, and commenting down below. Thank you. See you in the next video.